Well, today we're going to take a look at something rather unusual that always intrigues me whenever I return to look at it. And we'll see how this unusual probability distribution, that's sometimes known as Benford's law, how it arose, why it's a reasonable thing to expect to be true about numbers that you encounter in real life, and then some of the unusual applications that have been made of the idea to accountancy and other matters of everyday life. Well, the first person to notice that there was something rather unequal about numbers, or certain bits of them, was Simon Newcomb. Newcomb tends to be famous for making one or two rather bad predictions. He sometimes bears the blame for saying that he believed that heavier-than-air flying machines were an impossibility. And he also said in 1888 that we're probably reaching the limit of all we can know about astronomy. Well, he was actually rather a good astronomer for all that, and like many intellectuals of the period, very much polymath, someone who worked in all sorts of different areas of science and mathematics. And in 1881, he wrote a little paper, I think it appeared in Atlantic Monthly or something like that, Atlantic Mathematical Monthly, which had the title On the Frequency of Use of Different Digits in Natural Numbers. Sounds a bit strange. And he said he was motivated by taking a careful look at his log tables. When I looked up log tables on the internet, I found I didn't own a set of log tables anymore. And when I looked it up on the web to see if I get a picture of a set of log tables, I got these offered to me. Anyway, I then moved on and found these. People beyond a certain age will remember these. They are a complete mystery to anyone under a certain age. So if you do mathematics at school today, there are certain things like log tables and a slide rule which you'll never see, you will probably never heard of. But when I was at school, were the only thing that you really needed in order to be able to carry out any calculation. And these log tables of Newcomb's, he noticed, were always slightly more worn for the smaller numbers. And you can see it on this page. They're sort of more thumbed down here than they are down here. And this made him suspicious that somehow there was a different frequency distribution, other than just the uniform one, for the occurrence of particular digits in the first digit place of numbers that you tended to come across and use. So what he's noticing here is that people were tending to look up the logarithms of numbers that began with 1, okay, rather more often the numbers that began with 2 and 3, and certainly much more often the numbers that began with 8 and 9. So this sounds very odd, and led to what I call Newcomb's law. He said that the 10 digits from 0 to 9 do not occur with equal frequency. And he said that this is evident to anyone making use of logarithmic tables, and you notice how much faster the first pages wear out than the last ones. And he then says rather more particularly the first digit of a number. So if you take the digit after the decimal place, for example, you don't worry about whether the number is plus or minus. So a number minus 3.1414, the first digit would be 1. And he said it's more often 1, that first digit, than any other digit. And then the next most common one is 2, and then 3, and then 4, and so on, up to 9. And he then noticed that there is a good reason for this, and that the probability distribution of the mantissa, that's the fractional parts of the logarithms, that they're equally probable. So it's like saying that if you change the numbers into 10 to the power x, as it were, the distribution of those x's in the power is uniform. So let's look at this in a number of different ways, and we'll sort of prove it really later on. So what he's saying is that the data on the first digits are evenly spread out if you use a logarithmic scale. Well, log 2 is 0.3010, okay, so he's saying 30% or 30.1% of numbers, the first digit is a 1, and then you work down. This is the probability for the digit being 2, and then 3, and then 4, and so on. So his evident law is that the probability distribution for that first digit looks like the log of so the probability that it's d is the log of d plus 1 minus the log of d over the log of 10 minus the log of 1. And this is just in base log 10. Okay, this is the log of 1 plus 1 over d. So that's this rule here. So the probability that the first digit is a 1 is the log of 1 plus 1, which is the log of 2, 0.3. The probability that it's 2 is 1 plus 1 over 2, log of 1.5, and so on, all the way down to the log of 9 occurring, 1 plus 1 over 9. You can see that something odd is going on here, that the distribution of the digits is not uniform. The situation is rather like having a clock face with the numbers 1 to 10 marked around that dial. And as you go to larger and larger numbers, of course, you first meet 1, and then you go all the way around to 9, then you come back to 10, 11, you start to get more numbers beginning with 1 again. And as you go round and round and round this circle, eventually, in the long run, the distribution of the appearance of any digit is uniform. But it's uniform on this circular distribution, not on the simple counting linear distribution. So this is the distribution that Newcomb first proposed and that we've just written down. The probability of the first digit after the decimal place, say of a number here being equal to d, is this distribution here. If the number, as it starts to get large, as you're getting up to a ninth, the log of 1 plus something, if the something is small, is just equal to the something. Okay, it's a Taylor expansion. So when d is getting up towards 9, this is beginning to look like 1 over d. So here is the distribution as a bar chart. Okay, log 2 up there, log 1.5, and so on all the way down to log of 1 and a ninth, 10 over 9, down the bottom. So the obvious thing you notice about this, it's not as you would have guessed at all. So if someone had stopped you in the street and you didn't know about this and asked you what's the likelihood of any number that you start to pick out of the newspaper or pick in the lottery or somewhere else, random, having a first digit equal to 2 or equal to 3, you would have thought that the probabilities would all be the same and that they would all be just equal to about 0.11111. So they're all equal to a ninth. But Newcomb's claim was that's not the case at all. This is what his distribution tells you for these probabilities. So to 2 decimal places, 30% of numbers that you just pick at random in some way, some controlled way, 30% of them are going to begin with 1s. So you can see you might win a lot of money if you knew this, and other people didn't. Nobody took much notice of this in some sense of writing papers about it. I think most people felt that it was fairly obvious, it was fairly reasonable at the end of the 19th century. There's not much more to say. And it was just forgotten. And then it was rediscovered in 1938 by this gentleman, Frank Benford, who was an electrical engineer working at GEC in the United States. And he made essentially the same discovery, but he decided to test it out much more systematically by gathering up all sorts of collections of data and numbers and seeing whether the result was really true. So he derived this same distribution. He didn't know of Newcomb's work before. And it's as a result of this that it became known as Benford's law. Sometimes I'll call it the Newcomb-Benford law. Sometimes I'll just call it Benford's law for short. His paper was called The Law of Anomalous Numbers. It's probably not a good title, in that it's really, the numbers are not anomalous at all. And this is a collection of some of the things that Benford gathered. He gathered nearly 20,000 pieces of numerical data and tested them out to see if they followed this law. So using his atlas and geographical information, he looked at lists of the sizes, the areas of all the leading lakes in the United States and the American continent and in Europe. And he wrote down the numbers for the areas, and then he looked at the first digit after the decimal place of those areas. So this is a big sample of information of the same sort. It's information that's got units of area. And he finds, lo and behold, 31% of the river areas have got 1 as their first digit. And then here are the others, all the way down to 9. He then starts looking at the baseball averages for past seasons, systematically recorded in the US, rather like Wisden gives you information about cricket averages and so forth. And so he starts looking through those and seeing what the batting averages and the bowling averages and so forth are for players as back as far as records have kept. And again, he's got the same trend. He's got 32.7% of those numbers beginning with a 1. Next, he just looked through random magazines, and every time a number appears in the magazine, other than the page numbers, but if it tells you that you know, footballers have been transferred for this amount of money today or whatever, or they're earning this. So he just makes a note of any numbers that he comes across in magazines and newspapers, and you can see again it's not exactly 30, but there's pretty much the same trend. It's rather spooky. Then he does something systematic. He just says, well, let's work out all the powers of 2. 2, 4, 8, 16, 32, 64. Just keep on going to generate a huge list of numbers that are just powers of 2. What happens there? Well, you get bang on your 30% of them start with a 1 and down to 5. He then started looking in the world of physics and engineering. At the back of his book, all those tables about the strengths of materials, the coefficients of expansion of different metals, all the standard properties that you find in a book like Kay and Leiby or Brownowitz and Stegun or whatever. And he just makes a frequency distribution from those. And again, exactly the same type of answer. 30.6% of them, first digit is 1. Next, he does something physics. He looks at the half-life of all sorts of radioactive materials against alpha decay. And it's 29.6%, so this is a sort of real physical situation. It's governed by an intrinsically random quantum mechanical process, but there's also a systematic aspect of nuclear physics. And these are the predictions that you would expect if you followed the Benford-Newcomb law. And you can see the agreement is sort of good enough. There's something rather strange. I think it's supposed to be a 17. That's why that looks a bit odd. 17.7. But there's obviously something going on here. So is there some secret universal law of nature, as it were, which is behind this? Here are some other trials that people tried later. You just take the street addresses of all the people in your mailing list and look at the digits of the street numbers. Here's what happens. You do a lot of those from a big database. Pretty much the same story. 30% beginning with 1s. Here's some of the information in Benford's original list brought up to date. So Benford's law is the blue bar. Numbers in newspapers, the green one. The census data in 1990 in the United States. And this is financial information from Dow Jones day by day. And you can see again, it's pretty solid. Exactly the same type of trend. To rub it in, here's another one. Consumer price index variations, looking at the numbers being published, census, the birth rate. the areas of particular countries in the world, lottery winning tickets. And here's Benford's law with the solid line. And this dotted line is what would happen if the probabilities were just the same, if they were 0.11. Well, why does this sort of thing happen? Where does this magic 30% come from? Well, there are all sorts of ways of looking at this, and all sorts of people had different goes at trying to produce the most convincing way of looking at it. I think this is quite a good way of thinking about it. Suppose that you're picking raffle tickets, okay, and you're interested again in what's the probability that you have a raffle ticket where the first digit is 1. So it might be the ticket with number 1 on it, or 11, or 111, or 109, or something like that. Well, you can see if there are just 2 tickets in the raffle, okay, your probability of having a 1 as the first digit is a half. Okay, it's this ticket, but not that ticket. If there are 3 tickets in the raffle, the probability is a third. And so on. If you go up and you've got 9 tickets, numbered 1 to 9, the probability of having a 1 is 1/9. Okay, it's all very simple. But once you have 10 tickets, things change. A new number's appeared, and another number that begins with a 1, and the probability jumps up to a fifth, because there are now 2 candidates out of 10. 2 over 10 is a fifth. What then happens if we add a 11th ticket and 12 and 13? You can see the probability of beginning with 1 is steadily going up each time, because each of the new numbers begins with a 1. But once you get to 20 tickets, it's going to start dropping again, because all the new numbers don't begin with a 1. So what's happening to the probability of having a ticket that begins with a 1 is that at first, okay, the probability is up here, it's 50%. As you go up to 9 tickets, the probability drops. And then when you add the 10th ticket, it goes up to a fifth, 20%. You keep adding all the way up to 20, it'll go up all the way up to here. And then once you go between 20 tickets onward, it starts to drop, goes all the way down here. Then when you get to 100, okay, it starts to go up again. So you can see as you add more and more and more numbers, you get this funny falling, increasing, oscillatory change in the probability. So what this means, obviously, is the probability of having a ticket begins with 1 depends on the number of tickets. Okay? So what you might say, well, let's take the average. Let's suppose that it really is a huge number of tickets, hundreds and hundreds of thousands. What's the average of this funny spiky curve? Well, it's something that sort of goes somewhere through here, okay? But if you take the average carefully, it's 30.1%. Okay? So you can understand, I think, from this picture how it comes about that you get such a probability. If we were to run through the same argument for the 2s, okay, it would be slightly different, because with the 2 tickets we'd have a probability of 50% again, and then as you went all the way up to 10, you would still have no new case. You'd have to go all the way up to 12 before you got a new one, and then when you started with the 20s, you would have a rising probability. And if you carried out the same argument, we would get the other probability, the log of 1 plus 1 over 2, log of 3/2. So this is a simple argument as to why we expect this type of pattern to work. But there are 1 or 2 other ways of looking at that distribution of Newcomb and Benford's. It has to have certain properties. Most of the quantities that we looked at for candidate numbers, let's take one like the areas of the lakes in the world that Benford took. Now that's got units. When he did it, he probably worked them out in square miles. But if there's a universal distribution about digits, it shouldn't care whether you're measuring the areas in square miles or square kilometres or square inches or whatever. And what that means is that any universal distribution governing such things must be invariant under multiplying it by some overall factor, every piece of data by some number, which would be the conversion factor, say between square kilometres to square miles to square inches. And what that means in sort of more formal mathematical language, mathematicians would say the distribution has to be scale invariant. So if you scale all the numbers by multiplying or dividing them by the same factor, you must get the same overall result. And what this means is that if there's a distribution for these first digits of numbers which have units, then the probability distribution of a number multiplied by a constant, let's call it k, has got to look the same as the probability distribution for the numbers, just multiplied by some overall factor. Okay? So the shape of the distribution doesn't change. It's just like looking at it under a magnifying glass or under a microscope. It just scales. Well, probability distribution, so if we integrate p of x over all the x values, we get 1. And so that means if you substitute x for kx, the integral of kx over all the x values would have to be 1 over k. And that tells you that this little factor here, the multiplying factor, is just 1 over k. And so if you put 1 over k there, and you integrate this, this is equal to 1 over k, this is equal to 1, and that's 1 over k. If you now differentiate this with respect to kx, you end up with this rather simple little differential equation here, differentiating a product, put k as 1, and you know immediately that p must just be 1 over x. So the answer to this little problem is that the function p is just of x is 1 over x, so this is 1 over kx is 1 over k times 1 over x. So the requirement that the distribution be scale invariant, that it doesn't care about the units in which you measure quantities that you line up in your tables, as long as you measure them all in the same units, okay, so you must have all the areas in square kilometres and all the sums of money in pounds, as it were, the probability distribution that we're looking for is 1 over x. There's a detail here in that if you did indeed try to check this, if the distribution went all the way from 0 to infinity, we'd have a problem here, because this would be the log of x, and the log of infinity is not 1, it's infinity. But in practice, when we do these problems and look at these numbers, we don't go all the way to infinity. The areas of the lakes have a finite maximum size, and they don't go to 0 either. So what this tells us is that the probability of the first digit being a d is just the integral of this distribution from d up to d plus 1, so that's the next digit. And in order to normalize, so it's a probability, we integrate the probability all the way from 1 up to 10. So this is the probability that it's in this little interval, and that's the probability that you're in the whole interval from 1 to 10. So if you work that out, integral of 1 over x is log x, so this is log of d plus 1 minus log d, divided by log 10 minus log 1, and that's just log of 1 plus 1 over d. And that was the result that Newcomb guessed, in a sense, just by common sense, rather advanced common sense, and Benford was also able to work out. But here we see it arises as a requirement that things be scale invariant, invariant under changing the units in which you do the problem. Other people, after Newcomb, and Newcomb wondered about this as well, what would happen if you thought about the second digit in any old numbers you tend to gather up? And it's clear that there's going to be a distribution for the second digit. Okay? In fact, there's such a distribution for any digit. So the probability, for example, of the second digit being a 3 is just the sum of the probabilities of the first two digits of the number being, could either be 1.3, couldn't it? Could be 1, 3, It could be 2, 3, it could be 3, 3, it could be 4, 3, all the way up to 9, 3. So they're the possible ways in which you could have a combination of first and second digits so that the second digit was a 3. And so if we look at our logarithmic spread of the possibilities from 1 up to 9 and up to 10 here, the probability of having these situations is just this little patch here, between 1.3 and 1.4, between 2.3 and 2.4, and all the way up. And the overall probability you want is just the sum of all these. Okay? So the fraction, for example, in this little niche 1.4 to 1.3 is just the log of 1.4 minus the log of 1.3 over log 10 minus 1. It's just 1. So it's the log of 14 over 3. So you just do the same thing now, same little calculation to find what's the probability of being in the next little interval here, and then the next one, the next one, the next one, and add them all together. So there's nothing very difficult about this. It's a bit laborious. Here's what we know already. The probability of the first digit is the log of 1 plus 1 over d, and that for the second digit is going to be the sum of the probabilities that you're always in these little intervals. And Newcomb himself understood that. Okay, so you can work out, if you wish, then you can go to the third digit and so on. The interesting thing about this that this then reveals is what statisticians will call the joint distribution. That's what's the probability the second digit has a particular value given that the first digit has another value. That this probability is not independent. So the probability that the second digit has a particular value and the first digit has a particular value is not just equal to the product of the separate probabilities for the first and second digits. So the second digit probability depends on the first digit probability. So, and this is the expression that you get. It looks rather messy, but it's really rather simple. It's just an awkward way to write it. So suppose you had the fractional part of pi. Okay, so 3.14, let's call it 0.314. What's the probability that the first digit is 3, second digit is 1, fourth digit is 4? And what this means, it's just 1 plus 1 over 314. And the probability is 0.0014. So 0.1% that you have this particular combination. You can then start thinking, well, what would happen if there wasn't any conditioning? Okay, the unconditional probability up here that the second digit is 1 is 0.109. The first digit it's 0.30. Okay, but the conditional probability that it's 1, given that the first is 1, it's a little bit bigger, 0.115. As the number of digits increases, the dependence of, say, the second digit on the first falls off, and they become increasingly as if they're just independent. So rather quickly, as the number of digits in the number gets bigger and bigger and bigger and bigger, what this formula tells you is that the probability just becomes equal to 1 over the number of numbers. So it becomes uniform. Okay. Because the log of 1 plus something small just looks like something small. Well, we've seen that Benford's distribution gets picked out by this criteria that we want things to be scale invariant. It gets picked out also by another requirement that you might imagine you would want. We've been always talking about taking numbers out of the newspapers, looking them up here and there. There are always cases where we would be using our ordinary base 10 arithmetic. But you might think, if there's some universal distribution governing first digits, why does it care what base of arithmetic we're using? Surely you ought to get a similar sort of result by using any base of arithmetic. And that turns out to be the case. I won't go through the algebra, but you can show that the only distribution that you could get which would have the same form, the same shape as it were, irrespective of base, is this one. So if the arithmetic base is b, okay, where b needn't be 10, then what happens to the first digit distribution is that it approaches this Benford form, but with the logarithm to the base b. Because all that's happened on the denominator, remember we had that log 10 minus log 1 factor, you just have log b minus log 1. So here's a picture. Okay, here are the probabilities, leading digit. Here was Benford's law, and if you change the base of the arithmetic, you just get a collection of distributions that have the same basic type of shape, same form, but with slightly different numerics. But although these two invariances pick out Benford's form of the law, in some ways you think, well, why should there be a distribution like this at all? It doesn't really tell you why there is a distribution or under what conditions you would expect there to be such a distribution. And if you look far enough on the web, you'll find mysterious speculations that Benford law is the secret of the universe, some deep secret about numbers. Well, not everything follows Benford's law. So interesting to try and understand then why that might be, because it might be the key to understanding why it is so ubiquitous. So here is a collection of numbers taken from United States tax returns and the first digit of sums of total income and so forth. And you can see it follows the leading digit Benford law pretty well. But here's a collection of results from a random number generator. Okay, huge numbers of randomly generated numbers. You can find such things on the web, and sometimes people need such numbers for various purposes. And you can see that these numbers do not follow Benford's law. Here's another example of something that doesn't follow Benford's law, which we met a couple of lectures back, last lecture maybe, when we had a look at continued fractions. Remember, we could expand any real number as a continued fraction in this staircase of descending fractions, and this collection of whole numbers here can be listed, and they give a unique definition of the real number. If the number is irrational, okay, then this continued fraction never ends. And remarkably, there is a probability distribution which holds for the distribution of these numbers, which is true for almost every number in a rather precise sense. And what that probability distribution is the probability of the whole number, or the digit k, appearing here is given by this probability distribution here. This is a natural logarithm, 1 plus 1 over k times k plus 2. So you remember what the Benford one was, 1 plus 1 over d. So this is not the same, but it shares many features. Again, the number 1 is most common. 41% of continued fraction numbers are 1s, and 17% are 2s, and so on. This distribution, when k becomes very large, again, it's the log of 1 plus something that gets small. Log of 1 plus x, when x is small, looks like x. And so this thing, when k is big, it's 1 over 1 plus k squared. So this distribution looks like 1 over k squared as k gets very large. Slightly steeper than Benford. Probabilities fall off much faster. So this is another non-Benford distribution. Well, it's possible to understand in a fairly clear way what you need of a list of numbers in order that they're going to be Benford distributed. We want the data that we line up with all these digits on to measure the same thing. So we take a collection of areas, a collection of prices, but we don't mix all those things together. So they all have the same type of unit, so that when you scale them, you would only change square kilometres into square miles or acres or something like that. You also want the distribution of the numbers to have no sort of built-in maximum minimum, so it would be skewed in some way. So if you took people's heights, probably wouldn't be a good candidate. There's in effect a maximum for adults, and there would be a minimum, typically in any sample. So you want distributions that really have an enormous range. And you don't want the numbers to be assigned in some pattern which skews the story. So phone numbers are no good. Because if you drop the 0, you know, my phone code's 1223, and so they tend to begin with 1s, and then there's a part of the country where they'll begin with 2s, in London and so on. So those sorts of numbers which are orderly in some pre-assigned way are not useful for this purpose. You also want the underlying distribution to be pretty smooth across all the possible numbers. So you don't want someone to say, right, in my collection of data, I don't allow any numbers to begin with 5 because I'm suspicious of numbers where the first digit begins with 5. You know, so there might be someone who picks their lottery numbers because they've got some secret prejudice against certain numbers. You know, they never put in 13s or 12s, or so they don't like teenage numbers, so they don't put them in. Also, a good rule is in real distributions is that there tend to be more small things, more small items than large ones. So with the lake areas, for example, there are more small lakes than there are large lakes. If you were looking at the sizes of grains of sand and rock on the Earth, there are more small ones than there are large ones. But most important of all, in some ways linked to some of these things, we want the data to span a large range of values. So if we were to take the numbers in the data and sort of re-express them as 10 to the power something, so instead of 100 we'd say, right, that's 10 squared. What we want in the data is that those powers really span a very large range. Certainly a range that's much bigger than the distance between individual digits. So if all the data is sort of crammed in around 10 to the power 1 up to 10 to the power 1 and a bit, there's just not enough range to explore this probability distribution. So what you would say is that the distribution must be broad rather than narrow. It must spread across a very wide range of values. So, I mean, here are two examples. So here is a broad distribution, okay? And here are numbers along the bottom, sort of expressed in this type of logarithmic scale. And what you want here, this red area is exploring the numbers where the first digit is 1. So these are numbers between 1 and 2. And then here you're going up, you've reached 10. So these are the ones from 10 up to 19, 100, okay, up to 119 and so on. So each time you see a red area, then it's the probability that the first digit is a 1. And the blue has been put in here. That's another example. This is where the first digit is 8. Okay? So it's a bit like the first thing we did, taking the averages. And here's another type of distribution for all the numbers. Okay? So this is really very narrow. I think this was probably something like the sizes of electoral districts in California or something, which is engineered, you know, so that they're all a bit the same size. So in some sense there is a maximum, and they've been deliberately chosen, so there's about the same number of voters. So that's why it's very narrow. And again, you can see this is the first digit being 1, that probability there in the red, and this is the one for the 8. Now this distribution, you see the whole distribution is so broad that it covers many, many multiples of the coloured bands. So you have a chance for the distribution to be reached. Here the distribution doesn't. Secondly, the probability is equal to the area under the curve. And up here, the area is nicely proportional to the width along the bottom. But here, the width is not a good guide to the area. because the width is so small compared with the height. And so the area under this curve is dominated by the height of the curve, which is determined by this very steep, narrow distribution. Whereas here, because it's broad and rather shallow, the width, this probability, this width here is a good guide to what this area will be. Or the relative probabilities are well indicated by the relative widths of these bands. So a good example, this would be the case for numbers that you were generating from incomes of large numbers of people, from populations of countless countries of the world. They have a very large range of sizes. Whereas here, something like human heights, IQ scores, populations in small electoral districts that are well defined and engineered in size, they will have this narrow distribution and a non-Benford distribution. So here are some pictures of data which some cases is like or are like the last case and some not. So this one up here is population of countries of the world. Okay, so this is what the population looks like against number. But if we look at the frequency against the log of the population, okay, it's really quite nice and broad. Distribution is much broader than the individual slots here. And so when you look at the leading digits of this, it's a broad distribution, you expect it to approach Benford, and it does. Okay, so the first digit distribution follows Benford. Another example, this is jackpot numbers, US Powerball game. Again, if you look at the frequency of various first digits arising on different numbers, okay, and the range of numbers, it's a nice broad distribution. Okay, all the possibilities are explored pretty randomly, uniformly, and accordingly you get a Benford distribution for the first digits. But here's the little districts, okay, the congressional districts in California in the previous distribution. When you first look at the frequency versus population size, it looks a bit odd. Okay, it's quite flat. And then when you look at this on a logarithmic scale, it's really very narrow indeed. Okay, they're all roughly the same size, and so there isn't a probability distribution that spans lots of decades on the log scale. There isn't room for the probability distribution to be explored. And so the leading digit distribution really doesn't, it's these bars here, it doesn't look like Benford at all. This one at the bottom is cities in California, population sizes. Again, it's quite good. There's a steep but reasonably broad distribution on the logarithmic scale, and things follow Benford fairly well. So we have an understanding really now as to how and when you should expect to find a Benford type distribution. You want a nice broad underlying distribution, no skewing with maximum minima or special limitations. What does this tell you about winning lotteries? Well, fairly obvious really. I mean, so here's one, here's a small lottery in America, the Massachusetts numbers game. You just bet on a 4-digit number there, which is generated at random, and all the people that guess the right number share the jackpot. I'm not sure whether they had a second round where they then put you in and you picked another number or something like that. But you can see there are going to be lots of winners here. It's not like our lottery. And you're not going to win much because you tend to share a lot. And as our children used to say when they came home from nursery, it's nice to share, Dad. I was usually eating an ice cream or something like that at the time. So what should your strategy be? Well, you might have in mind that you don't want to share the jackpot, or you want to share it with as few other punters as possible. So you want to try and pick a number that's less likely to pick by others. Well, suppose that all the entrants, the others, pick their numbers from one of these Benford-like collections of numbers drawn from their experience. So they don't pick them at random, but they pick them from the newspaper or something like that. They don't pick them from birthdays. That would not be good. So what would then happen? Well, they're most likely to pick numbers, the first digit of which is 1, and we've seen that we know the probability of the second digit, third digit, and so on. So what you should do is to pick numbers that are the opposite of the Benford probabilities. So you should pick numbers that begin with 8s and 9s, because they would have the lowest probability of being occurring in these naturally occurring collections of numbers that people may be picking out of their experience. There was a curious psychological experiment carried out by Hill some years ago in the US, Theodore Hill, who was a mathematician, just looking at what numbers people chose in psychological experiments when they were asked to pick numbers at random, okay, with many digits in them. And curiously, the probability was weighted very much towards people picking numbers that began with small digits. Don't know why that is, but it gives you more confidence that if you pick numbers that begin with large digits, you have an even better chance of winning the prize outright. As with most things in mathematics, you can have too much of a good thing, and once people find one rule, the first reaction to it is, can we generalize it? Can we see it as part of something that's bigger and maybe better or has more applications? And we've seen that Benford's law is really a probability distribution for an underlying process where the probability of having the result x is proportional to 1 over x. So as x gets big, there's a smaller probability. And that's the distribution that has those nice scale invariant properties and base invariant properties. And when we integrate this between d and d plus 1, we get this Benford distribution for the first digit being d. But you could say, well, suppose we forget about Benford for the moment and we'll be interested in processes where the probability is not 1 over x, but 1 over x to some power, which I call a, and particularly in the cases where a is not equal to 1. Well, if you do what we did before for this rule and integrate this between d and d plus 1 and normalize the probability so the integral is 1, you're interested in this. C is the normalization, and you can do the integral very easily, more easily than here actually. So the integral is x to the 1 minus a divided by 1 minus a. And you evaluate at this limit and that limit, take them away, and you've got this simple little formula. If a was 2, for example, so it's a rather steep distribution now, the probability of the first digit of 1 will be 0.56. If you want to know probability of being 3, it's already down to 9%, and it's 1% for d is 9. So you can see the general effect that when this is steeper than Benford, there's even more chance of the first digit being 1. The interest in this is that one application of a Benford-like approach is to think about the prime numbers. So whenever you have something about numbers, some probability theorem, you always wonder, well, what is it telling you about prime numbers? Does this tell you something new about the prime numbers? So if you write down all the prime numbers and you take the first digit in the prime numbers, okay, so you've got 2, 5, 7, 11, so you've got one there, 13, 17, 19, and so on. So you can see how it's going to go. It's like the wraparound graph. What happens? Well, the probability distribution for the first digits in the prime numbers does not follow Benford's law. Not quite. It follows this law, but the value of a, okay, depends on how many numbers you've been looking at. So if you look at all the prime numbers from 1 up to n, the first digit distribution is very well fitted by this rule here. So a looks like 1 over the logarithm of n minus 1.1, basically. So it's just a little offset. So here's the picture. What this is telling you is that as you go, okay, to very large numbers, as n becomes very, very large, these first digits are just evenly distributed. Okay, so there's no bias towards any number at all. But the approach to that distribution is very well ordered. So here is the percentage. Okay, we're just plotting this rule here for p of x for the first digit distribution. The solid curve is that rule, that mathematical rule, and the dotted line is the data from the prime numbers up to very large n. And you can see it really does fit extremely well with a value of a equal to 1.1. So the prime numbers don't quite follow Benford's law. That would be 1.0, but they follow a similar type of law as you approach their uniform probability distribution. Well, the last few slides I want to show you how people have rather imaginatively thought that they might use Benford's law to detect fraud, false accounting and sort of spurious tax returns, and these gentlemen here are sort of key players. So if you believe that Benford's law is rather ubiquitous, so long as your distribution is broad and is not biased in particular ways, maybe it will give you a way of telling whether people had sort of manipulated or doctored the collections of numbers that they're giving to you as pieces of evidence or their financial records. And this idea occurred first to Mark Nigrini, who was a graduate student at the University of Cincinnati, which I guess in Ohio, isn't it, back in 1992. And his PhD thesis is called The Detection of Income Evasion through an Analysis of Digital Distributions. And what he did, first of all, was to look at huge numbers of IRS, American Revenue Service, files to explore the extent to which Benford's law was well followed. And overall, in this huge mass of data, it was followed really beautifully accurately. So the large mass of income tax returns in the US, which he had access to, followed Benford's law for the first digit and then for the second digit as well, really very well. And then he had access to data which was known to be fraudulent. And this was mixed in with other real data by the people who he was working with. So it was sort of double-blind experiment. And he correctly identified the false returns by the fact that they didn't follow Benford's first digit law. So they tended to have rather odd distributions. So here is Benford's law again in the blue, okay, 30% with digit 1, and here's 17% here, and so on. Here's the good tax data, or so he believes, which are the green bars, and you see they follow Benford really rather well. Broad distribution, huge amounts of data spanning all the range of values. Here's the fraudulent data that he was given, the brown distribution. It's got loads more 5s and 6s. It really sticks out like a sore thumb. Somebody obviously likes 5s. Yeah, they probably think, oh, in between 0 and yeah. And then here's the random data, which is pretty much 0.11 all the way across. So this excited the chief financial investigator of Brooklyn District, and so he gave a sort of press conference, had all sorts of meetings with Nigrini, and here's his sort of account of those 7 cases. We used them as a test of Nigrini's computer program. It correctly spotted all 7 cases as involving probable fraud. And then something rather interesting happened, because years after this all became rather well known, the Clintons, after much controversy and criticism about their financial affairs, published their tax data, their tax return. And so Negrini thought that he should analyse their tax returns. And that he did. And the $64 million question is, what did he find? Well, it was all okay. So the Clintons' tax return data followed Benford's law rather beautifully. So disappointing, but true. Thank you. Thank you. There's time for a few questions. You have to wait for the roving microphone to reach you. And it's up the back.
Presumably the anti-logarithm tables would be equally well thumbed.
Yes, if only I had a set of log tables still, I could tell you. Go home and check. But seriously, you can see, you can now spend many happy hours checking this out. It's a nice project, so if you're a school student and you're looking for an interesting project, think about some situations or publications where numerical data appears, and gather that data, forget about what happens before the decimal place, take the first digit after the decimal place. Does it follow the Benford law? Are 30% of those digits ones? If not, can you understand why not? What is it about the distribution that breaks the requirements? But if you just pick up your newspaper, every time you see a number mentioned, whether it's Cheryl Cole's inside leg measurement or Wayne Rooney's salary or something, just note what the first digit is and see what happens. They have to have the same units, you know. Gentleman down in the front row, and then I've got the gentleman to the left, my left. Okay.
Could Benford's law have been applied to the expenses claims in the House of Commons?
Probably not, because there was supposedly a maximum, wasn't there? But it wasn't necessary.
Just think about it, using it for fraud detection. I understand why if you take a totality of income and other expenses data, it will follow Benford's law. But for any one individual, then A is a far smaller data set, and secondly, there are likely to be correlations between the data. So surely there's a chance of a large number of false positives. Whilst it might be good at identifying frauds, you showed in the previous slide, if you also had true data on an individual basis, there'd be a large number of false positives as well, wouldn't there?
Yes, it's a good idea. In fact, people who do this sort of thing tend not actually to pick on the first digit. They pick on the second digit and say the third digit, and then look at the cross-correlation. So they gather much more information. Where this has been done recently, but with sort of controversial results and no agreement, people started using this technique to analyse the publicly announced results of the Iranian elections. And there was some argument about, so the first claim was that they did follow Benford's law quite well, and then other people claimed that they didn't if you introduced other constraints into the problem that you knew existed, and then somebody else said, but they match what the results were for previous elections for a long period of time statistically. So it's by no means clear cut. This is not a sort of golden bullet. It's an interesting thing to try. Okay, so if something does follow this distribution, probably all right. It means that the person putting in their return knows about Benford's law and has made sure that they run the little programs, Benfordize your tax return. So the Inland Revenue perhaps should be recommended to completely change their computer system to make sure they're sensitive to this. Keep them busy for 100 years, but yeah.
I'm speaking on behalf of the digit 0.
Yes.
and feeling rather unloved and neglected.
Yes.
There's certainly one case where you were talking about the second digit and subsequent digits where I can't see how you can legitimately exclude it. Also, if it's the first digit, presumably if you put on leading zeros, it's going to alter the whole thing again. And
Yes,
what do you get if you start taking zeros into account?
Yeah, you're just shifting along here to, so if you're going round in a circle, okay, your 0 is like the 10 with the first digit of the 1. So you just shift everything along so that you get the first non-zero digit. One more.
Thank you. Does Benford work for Roman numbers?
The Romanesque question. No. So Roman numerals are not a place value system. So the position of the numerals doesn't carry information. So 111 means 3, not 111. So I think you need a place value system to play this type of game. Okay, thanks very much. Bye.